Pure mathematics deals in absolutes. If you add 2 apples to 2 more, you have exactly 4. There is no margin for error. But the moment you move from the chalkboard to a scientific laboratory, that absolute certainty disappears. Every measurement of a physical quantity, no matter how advanced the tool, involves some degree of error. In science, a number isn't just a value, it's a statement about the limits of our equipment. Look at a high-precision digital scale. Often, that final decimal place refuses to stay still. It jitters between 2 values, because the instrument has reached the edge of what it can reliably detect. We call the steady digits reliable. These are the numbers known with absolute certainty. But we also include that final fluctuating value, the first uncertain digit. It marks the exact point where our measurement transitions from a known fact to an estimate. By combining these reliable digits with that one uncertain digit, we create significant figures. This specific count tells any other scientist exactly where the certainty of your measurement ends. To see how this works in practice, let's look at a common laboratory experiment, timing the swing of a pendulum. If you time an oscillation at 1.62 seconds, you make a very specific claim about precision. The 1 and the 6 are certain, but the 2 is an estimate. Because we have 2 certain digits and 1 uncertain one, this measurement has 3 significant figures. Now consider a different tool. You use a ruler to measure an object, recording a length of 28.75 centimeters. Here, the 2, 8, and 7 are certain. The final digit, 5, is the uncertain one. This gives us 4 significant figures. This limit is defined by the instrument's least count, the smallest interval the tool can actually sense. Reporting digits beyond that first uncertain one is misleading. It implies the tool is far more precise, which can quickly lead to massive cascading errors in all of your subsequent calculations. In physics, we often shift measurements between units, changing centimeters to meters or millimeters to fit a specific formula. This raises an important question. Does changing the units on paper actually increase the precision of the measurement you took in the real world? The rule is strict. A choice of change of different units does not change the number of significant digits or figures in a measurement. Take a length of 2.308 centimeters. It has 4 significant figures. If we convert this to meters, it becomes 0.02308. Those leading zeros are just placeholders to locate the decimal point, so the count stays at 4. If we convert it to micrometers, we get 23,080. Following the standard rule, trailing zeros in a number without a decimal point are not significant. This zero only scales the number to the correct unit. When we stack these values, we see that the core digits, 2, 3, 0, and 8, never change. They are the only digits that represent the actual physical interaction between the tool and the object. To avoid this confusion entirely, scientists use scientific notation. By expressing the value as 2.308 times 10 to the negative second power, we ensure that only the truly significant digits are reported. Significant figures serve as a permanent record of a measurement's original scale. They ensure that the precision established by your physical tool remains consistent, regardless of how you choose to manipulate the numbers later.